Okay, hello everyone. The title of my talk is Recurrent Neural Network Control of a Hybrid Dynamic Transfemoral Prosthesis with EdgeDR and Accelerator. My name is Chang. I'm a PhD student at the Institute of Neuroinformatics, and my research topic is hardware acceleration of deep learning. And I'm supervised by Professor Zhiqi Liu and Professor Toby Delbruck. And this work is a collaboration between UDH, ETH, and Caltech. And Rachel Gallagher is a PhD student from Caltech working on legged robot control. And this work was done in 2019 Telluride Neuromorphic Cognition Engineering Workshop. So I'd like to start with the motivation of our work, which is to use deep learning in nonlinear control. So currently, there are over 200 kilo Americans with transfemoral amputation or above the knee amputation. However, there are limitations of current devices. So first, they are energetically passive. So amputees expend around 33% more energy. Secondly, they require heuristic hand tuning for every patient. It's very time consuming. So the advantage of using a powered prosthesis is that they provide net power to user, and they are capable of more dynamic behaviors. And moreover, the control method can improve safety and comfortability. So this video shows a powered prosthesis called Advanced Mechanical Prosthesis 3, or AMPRO 3, developed in Caltech. And the video shows a subject wearing the prosthesis walking on treadmill. And there are also limitations of current prosthesis control methods. So first of all, complex controllers are computationally expensive to calculate online. Secondly, human nonlinear dynamics affects prosthesis dynamics and are difficult to model. And our solution is to train an RNN controller running on a hardware accelerator, which is called EdgeDR, developed by me in the Institute of Neuroinformatics. So why do we want to use RNNs? So RNNs can imitate complex controllers with scarce training data. And RNNs have potential to be retrained on personal data to model human dynamics without hand tuning. However, RNNs are difficult to run fast. That's why we need a hardware accelerator to realize that. EdgeDR accelerator exploits spike-based temporal sparsity to reduce latency and improve energy efficiency by up to a factor of 50 times. So to give you an overview of this project, in this project, basically, we want to train and deploy an RNN to control AMPRO end-to-end. So it has 3 steps. The first step is that we need a subject wearing the prosthesis, walking for a minute, collect data, and then we train an RNN. And this figure here actually shows a gated RNN called gated recurrent unit. And another famous variant of this type of RNN is called LSTM. And the second step is to deploy this RNNs onto our EdgeDR accelerator. And the final step is to just control the AMPRO processes. And actually, this is the final result. So this is a short GIF animations. I will show you the full videos later. So I'd like to give you some background of the EdgeDR accelerator, which was designed to accelerate gated RNNs at the very edge. So first of all, what are gated RNNs? So there are 2 famous variants. The first one is LSTM, long short-term memory. The second one is gated recurrent unit. And in this work, we use the second one. And they are very useful in temporal sequence processing. And they are widely used in speech recognition and machine translations. And of course, in this project, we use it on control. However, the computation is usually on cloud. So if you look at all the famous services provided by the big companies, the translation and also the voice assistant, all the computations are run on cloud servers. So what are the benefits to run the RNNs locally on the edge? So first of all is that edge inference is immune to network failure. And secondly, you have less privacy issue. However, if you want to run an RNN on the edge, the latency is really critical. And that requires very high batch run performance of the hardware to do deep neural network inference. And there are examples of edge inference applications, for example, on-device speech recognition, and also like this project, human-in-the-loop robot control. So there are already a lot of state-of-the-art RNN FPGA accelerators. So one of them is called BBS. For those of you who are not familiar with FPGA, it's called Field Programmable Gated Array. So basically, it's a chip that is full of reconfigurable logic and macro cells like digital signal processing processors. So on this type of chip, you can build your customized hardware pipeline to accelerate any algorithm you want. This is not achievable on previous conventional general purpose processors like CPU and GPU. So by doing this, you can achieve much lower latency and higher energy efficiency. So in this previous state-of-the-art RNN FPGA accelerator, they exploit weight sparsity in LSTM to achieve acceleration, and they achieve state-of-the-art batch one throughput, 2.4 teraops per second. And this number is very important to achieve low latency. However, to achieve this impressive number, they have to use a high-end Area 10 FPGA. They have 8.2 megabytes on-chip memory, so that's incredible numbers. This size of on-chip memory is not impossible when you want to run a neural network on the edge. And the power is 19 watts, so of course not optimal for battery hour, and the cost is also very high. So let's look at how they actually how they actually achieve to run a big network on the big FPGA. So what we did is that they train a network with one layer and 1024 neurons with LSTM neuron in a single layer. So the layer has 6.4 megabytes of dense weight. And they do a compression and compress that weight by 8 times using pruning. And that ends up with 0.8 megabytes of weight on chip. However, this number is still expensive for most edge platforms. So if you look at all the microcontrollers, and most of the low-end microcontrollers only have like several hundreds of kilobytes of on-chip memories. So 0.8 megabytes is actually a very big number. So at the end, it seems like the DRAM, dynamic random access memory, is still needed for big networks on the edge. So it's not very likely that it can always buffer all the neural network weights on chip. So the performance is still limited by DRAM bandwidth. So our target is to build an accelerator called EdgeDR, and we want to use spiking delta RNN to reduce DRAM access. And also we want to exploit temporal sparsity in GRU. And our target is to achieve low latency of running large networks on the edge. And the accelerator must be scalable for any available memory bandwidth. And it was built for real world problems such as classification and control. So our target is to build to implement our accelerator on embedded platform called MiniZ. It has a small FPGA chip on it, and the power is only 2 watts, and the cost is also much lower. So why is RNN so difficult to compute? So RNN is effective, but it's not efficient. So the LSTM, gated RNNs like LSTM is used in many real-time applications such as autonomous driving and also gaming AIs, where latency is critical. So if we look at a simple RNN formulation, most of the computations are matrix vector multiplication. And what's the problem of this type of computation is that we need too many memory access. So if you want to get every single output of the output element in the output vector, you have to multiply the whole input vector with the whole row of this matrix. And usually in RNN, in big RNN, you have like 1,000 of neurons, and the size of the matrix will be 1,000 by 1,000. That leads to a lot of weights. And the problem comes from the memory bottleneck. So over the years, the development speed of processor is way ahead of the memory. So the speed of the memory is much slower than processor and becoming the bottleneck of the performance. And furthermore, if you look at the power consumption, an off-chip DRAM access can be 10 to 100 times more expensive than a computation in the processor. So that's why we came up with this solution, which is called delta networks. And the principle is to convert a dense matrix dense vector multiplication into a dense matrix sparse vector multiplication in order to save operations and also memory access. So traditionally, if you look at RNNs, usually the weight matrix is multiplied to the raw input, xt. And in the delta network, instead of doing that, we compute the difference between every two neighbor time steps. And we multiply the change of the input states with the weight matrix. And by introducing a threshold of the delta vector, let's say if the change of the input state is less than threshold, we just simply make this element to be 0. And every 0 element in this input vector leads to the saving of the whole column of the computations. So in this sample, we can save 25 multiplications, 25s to 10 multiplication and 10s. And actually in our experiments, usually you can save up to 98% of operations and the memory access. And based on this algorithm, we built our accelerator called EdgeDR. It sits on an FPGA chip on the MiniDAT platform. And the MiniDAT also has an ARM CPU, which is handy for you to run any other types of computations you want, other than the recurrent neural networks. So here's the result of our accelerator. So we benchmarked our accelerator with other commercial GPU platforms on audio dataset. So we evaluated on a spoken digit recognition task on the TI digits dataset. And we trained a big network, which has 5.4 million of parameters. So it is either 2-layer 768 neurons GRU or 2-layer 664 neuron LSTM. So if you look at the figure, so the horizontal axis is the time, is a frame, and the vertical axis is the latency. So as you can see, the EdgeDR burns only 2 watts, but can achieve comparable latency compared to GTX 1080, which is like over 100 watt GPU card. And it's much faster than the other embedded platform like Jetson TX2 and Jetson Nano. And here is the comparison table. So as you can see, we can achieve like 4 times lower latency versus other platforms and embedded platform. And if you compare exactly EdgeDR with a powerful GTX 1080, we have much less cost, much lower power, and comparable latency. And here's a demo of the accelerator on speech recognition. So of course, this type of applications, the latency is important, but not that critical. So we want to further explore the use case of this type of accelerators. So that's why we reached to the group from Caltech, and we collaborate on the project to use the accelerator to control the processes called MPRO. So originally, the MPRO was controlled by a PD controller. So the controller model human prosthesis system as 5-link bipedal robotic hybrid system. So it has impacts in walking, cause a discrete jump in velocities. And also it's a hybrid system because it has continuous phase, a stance and swing, and also a discrete dynamics because it has impact. So so as for the controller, so the human has to design periodic output trajectory offline for prosthesis that accounts for impacts. So if you look at this figure, so this green block called desired trajectory generator, it's a hand-engineered model that models how the prosthesis should walk, and it generates a desired trajectory. And the PD controller is designed to make sure that the actual trajectory of the motors on the prosthesis becomes as close as possible to the desired trajectory. So on the prosthesis, we have 2 motors. So this motor is the knee motor, models the knee of a human, and this motor is the ankle motor that controls the ankle of the prosthesis. And as for the RN controllers, what we did here is that we replace the PD knee controller and also the PD ankle controller with a single RN controller. So what the RN controller receives is the error of the position and also the velocity of the knee motor and also the ankle motor. And also it receives a flag, which is a binary signal indicating whether the prosthesis is in stance phase or walking phase. And the RN controller generates the torque signal that is applied to the knee and also the ankle motor of the prosthesis. So there are two main challenges. The first one is that we need low latency for the real-time control, and the latency requirement is 5 milliseconds end to end. So that includes the RN computations and also the microcontrollers on the prosthesis. The second challenge is that we need low power required for portability, and both challenges are addressed by using the EdgeDR accelerator. As for the detail of implementation, so first of all, we collect prosthesis data in walking experiments, and then we train our RN on collected data, and then we run the RN on the EdgeDR in real time. And the RN outputs are sent to the prosthesis BeagleBone Black microprocessor by an SPI interface to control motors. And here is a picture showing the setup. So as you can see, this is the BeagleBone board originally on the prosthesis to receive control signals sending from the Minitab through an SPI interface. And on the left side of the prosthesis, the BeagleBone plus a cape was attached to directly control the motors, and the Minitab is attached to the other side of the prosthesis to send the control signals to the microcontroller. So here are more details about the training of the RNN. So we use imitation learning, and we use RNN to mimic the PD controller. So as you can see, the input consists of position and velocity of the motors and also the swing phase. And the output is just the torque. And we use L1 loss function to try to reduce the error between the RN outputs and the desired trajectory. And here's the network structure we used. We used 2 layers of delta GRU plus 1 layer of fully connected layer to model the PD controller. And compared to previous setup, we didn't find exactly very similar setup to our project. And this is the only one we found. And they used RN to do gate phase estimation on exoskeleton. And what they use is a tiny 2-layer 8-neuron LSTM network. And to do that, they need 0.5 kilograms of computer attached to the body of the human. And in our setup, we use the RN to do the control on the prosthesis. And we use a 2-layer and 128 neurons LSTM. And that has 128 times more operations than this setup. And we use a 2-watt Minitab to do all the computations. And here are the key results. So we do offline and online evaluation of the RN controllers. So during the offline evaluation, we compare the torque of the PD and the RN on test set. So as for the data set, the subject wears the prosthesis and walk on flat ground. And we collect 210 seconds of training set, 70 seconds of depth set, and 70 seconds of test set. And this is our network. And the 2 plots shows the results. So the horizontal axis is the time, and the vertical axis is the torque. And the red lines is the RN output, and black dots is a PD controller ground truth. So as you can see, the red overlaps black well, indicates that the RN closely models the PD controller behavior. And during the online evaluation, which is that we implemented the network on the FPGA and actually having the subject wearing the prosthesis controlled by an RN controller. And we did this evaluation on different slopes. So during the training, we only trained the prosthesis on flat ground walk. So the black curve is a flat ground training data set ground truth, and the red curve is the RN experimental data. So as you can see, the slope walking introduced a disturbance in ankle motion and human dynamics, but the RN still tracked the knee trajectories well, showing it generalized well. But of course, the slope walking is not extreme. So the slope is just a 5 degrees slope walking. So to conclude, in this project, what we achieved that we realized a first project that has an end-to-end RN control of a robotic prosthesis functioning with a human in the real world. And also the first work to use hardware accelerated RN for real-time control. So for potential future applications, we want to build simpler models of complex controllers for efficient computing. For example, in reality, the size of the network don't have to be so big. The size of the network can be much smaller, like 2 or 4 times smaller. And plus that, we can also apply compression techniques like pruning to further reduce the size of the network. So it's promising to have a very simple network that can reduce the number of computes compared to a complex controller. Secondly, we want to capture non-linearities and complexities of human behavior to include in prosthesis control. So like RN model-based control. And finally, I want to learn individual human gait behavior to account for human intent in prosthesis control. So finally, I want to talk about some experience in Telluride. So the Telluride workshop is a workshop that aims to bring the organizing principles of neurocognition into machine intelligence and to use lessons and technology from machine intelligence to understand how brain works. And usually every year it has 4 or 5 topic areas, and it has 3 weeks plus a final demonstrations. So during our project, we spent about 2 weeks to have our first prototype. And it was just unlucky that before the night of the final demonstration, the circuit board on the M-Pro burned out and we couldn't achieve the demonstration. And here's a failure video of our demonstration. See, I can show this video. Yeah, so during the collection of the data set and also the test phase of this project, yeah, it was really dangerous for Rachel to ride that prosthesis, and she had to fell on the ground for many times. So here is the final video that was a success. So this shows the controller of shows the result of the PD controller that was originally implemented on the prosthesis, and this is the RN controller. Yeah. And this is the result walking on slope. And the top half of the video is a PD controller, and second half of the video is RN controller. Yeah. So as you can see, so from the view of the subject, she couldn't tell the difference between the RN controller and the PD controller. She felt the 2 controllers are almost the same. So because we use imitation learning, so theoretically you couldn't achieve better performance than the PD controller. Yeah, but at the end, this project validates our thought that it's possible to do an end-to-end control with RNNs, and it's more promising in the future that we use the RNNs to model the dynamics of the system and combine it with other model-based control methods. And that ends my talk, and I want to thank all the sponsors and people involved in this project. Thank you. That ends my talk.
Thank you very much.